Yeah. Okay. The last lecture of the multiplicative weight update method, what we will see is we'll see an application towards what's called the hardcore set lemma, which was proved by Padlaslo in the late 90s, probably the early 2000s. And it was actually a rediscovery of multiplicative weighting. Because another paper in which independently this is in the complexity theory CS community, and the multiplicative weight update method was one. We have seen all parts of, if once you state the problem and what it is, we have seen it fully. So what I will do, spend most of the time today's lecture is actually set the scene. Where it is applied, why is it? It will seem very, very different from a typical application of multiplicative weight update method. But it's a very interesting setup, so that's what we will see. So what are we interested in is, within complexity, we are trying to understand the complexity of Boolean functions. I have some function.
So,
Yeah.
the notes for this won't be.
So the notes for it, this is identical to what I taught this one. So I will put the notes for it in this one. Identical. There is the reason I didn't do it. I'm not doing it is for two reasons. One, it's easier for me to do it on the board. There's more space and stuff. Other one, the notes are far more extensive than what I'm going to do in class. I'm not going to cover certain things, so I thought it's better to see these notes than the notes which I do in class. The notes are from 2021. The notes have far more details in it. It's not that I taught it in lecture. After lecture, I wrote a whole bunch in the notes. Yeah. So the notes will have everything that I'm saying and far more. So we are looking at Boolean functions. This could be on any domain, but let's for now, this could be on any domain. Chi. Zero, one. And typically, we will think of chi as the domain to be the Boolean hyperplane. And one common theme in complexity is to understand, given a function, how hard it is to compute. But for that, you have to talk about what is the model of computation we are working with. So how hard is it? This is a common. Yes, and if you guys are doing the complexity course, you will be seeing there's a various notion of resources. There's, you can talk about the time complexity, the non-deterministic time complexity, the space complexity, and all. What we will talk about today, things might work in other settings also. We'll talk about the circuit complexity. We're going to think, and that's where it will be useful for us to look at this as the domain 0, 1 to the n. So we're going to ask, what is the size of the circuit C? So the C sits on n inputs, x1, x2, xn. It's an n input circuit, and C can contain the internal gates are. Let's assume the internal gates are AND gates, OR gates, and NOT gates. AND and OR, this could be arity 2 AND gates or larger arity. If only 2, then you have to get a K arity OR gate, you have to nest them, you have to build this one. That's not going to cost us a lot. So we'll assume these are the only gates allowed. And we are going to build the circuit list. So we're going to ask the circuit, and you know what a circuit is. These are AND gates sitting here. They're taking things like this as an OR gate, thinking, and they can reuse. This particular computation can be reused by 2. It has to, if you look at it as a graph, this should be a DAG. It should be a directed acyclic graph. Why is it directed? Directed is the edges are going from the inputs to the output variable. And it is acyclic because they cannot be a loop. So it's any circuit is a directed acyclic graph in which of these types, certain types of internal, there are the leaf nodes which are labeled by the input variables, there's an output gate, and all the other gates are labeled by one of these 3, the ORs, ANDs, and NOTs. Nots are gates which have just one input and one output. It's all the usual stuff we have, and what we are interested in is what is the minimum size yes of a circuit required to compute. You can want this by S of F or size of F sometimes. I think this is what Ram Prasad will do when he teaches circuit complexity in class. We can also ask how well, so I can give you a circuit and ask you how well does this circuit compute this one. So we can also ask, given a circuit C, and a function f, how well does C compute f? It seems like a strange question because either it computes it or not compute. There's only a Boolean answer to it. But we can think of asking on how many inputs does it get it right and stuff. So we'll assume that there's a uniform distribution on the inputs, and we'll define this quantity delta C comma f to be probability x coming from the uniform distribution on 0, 1 to the n of f of x not equal to C of x. Okay, that's the error of the circuit. This is the error of circuit F of, rather the average error on the uniform distribution of circuit C for computing the function F. Certainly a function F is said to be easy if for size yes, if there is a circuit that computes it exactly. We would like to understand when is it hard, that when does it not compute. Now there are degrees of hardness. So what does it mean? So that's what we're going to ask. How do we measure hardness? One is the standard notion of hardness, which at least the theory CS people study, which is worst case hardness. What do I mean by that? Let's say F is worst case hard for circuits of size S if for every circuit of size S, delta CF is non-zero. That is, there's no circuit of size S that actually computes. That means it's worst case hard. This set of size S is not capable to compute the function F. That's right. If for every circuit C of size less than or equal to S, we have actually let me call this epsilon to keep in terms with error. E and E. Yeah. We have epsilon C of F is less than or less than is greater than 0. So this is worst case hardness. But sometimes things can be even more than worst case hard. There's one notion of hard. Sometimes things can be much harder than worst case. It will be that there is no function in this class. There's no circuit in this class, which this only says every circuit will fail on some input. It might be that this function is actually so hard that every circuit will not just fail on one input, but will fail on some 1% of the inputs. It is not even capable of getting it right. This only says it's not right getting it on 100%. It might be that every circuit actually fails on 1% of the inputs. No circuit can get better than 99% of the inputs. And this 99% could be it could be 99, it could be 75. And if it's a Boolean function, it can't be smaller than what?
50%.
It can't be 50%, because certainly the all ones function or the all zeros functions, one of them certainly gets it. Right. So there's a very simple constant function which gets it correct on 50, because it's a Boolean valued function on 50%. What we would like to ask is, we're going to ask average case hardness. Is it, how hard is it on average? Is it basically, if the function was so hard that basically you can't do anything better than random guessing, this is an extremely hard function in the average. Or it could be, so there are measures of hardness. There's worst case hardness. So even among the things I want to discuss is average case hardness. So here we will say that F is delta average case hard. In fact, I'm going to call it delta. Start off with one definition, then we move to open. F is delta mildly average case hard. I could have just put average, but let me put mildly hard for circuits of size S if for every circuit C of size S, epsilon CF is at least delta. This says that no circuit can compute better than 1 minus delta fraction. There is, so think of delta as some 1%, 2%, 10% or something. It says not just worst case, but every such circuit is incapable of computing more than on this delta fraction of points. And then the other, this is already more hard than worst case hardness. Then the other extreme is actually, it's as close to random guessing. That is, this delta is close to half. There is actually errors on half. You can't make it half, but you can make it anything less than half. Yeah.
Is half the strict limit? Because I just feel that if C is large enough, then certainly you like even if you do it randomly, you would get some more than half right always. Right?
That is what we're going to ask. We will so firstly, there is a point at which you can always compute the function. That is, once you have the number of gates is 2 power n by n. Every function can be computed. Therefore, there you cannot expect this one. I am thinking of typically the size of the circuit being some fixed polynomial, say n square, n cube, and an arbitrary this one. One can expect, you're asking, can it be better than?
Yeah, I just feel like it shouldn't be like exactly half. It should be a bit better than.
It'll be a bit better than half, but what we'll show is you can come arbitrarily close to half. That in fact that's going to be you will see when we come to that. So there's another notion of hardness. This is the first notion of hardness. This is the first notion of average case hardness. There's another notion of average case hard, which is strongly average case hard. We'll say F is, I've used epsilon, I used delta, let's use rho. Okay, this is not going to be consistent with those nodes. The nodes will have a different delta. F strongly, let's use the strongly average case hard. For circuits of size S. Every circuit C of size S, epsilon C comma F is at least half minus. This is more, so think of you, basically the difference between this and this is, this one says I cannot compute it better than 99% of the time. This says I cannot compute it better than 51% of the time. One would ask, why do we have 3 different types of hardness? Notice the type of hardness we want. So right now, I don't know if which of you are taking complexity class. Typically, we would be studying the worst case notion of hardware. We just say it's not computed or so. That's fine, but when you're using hard functions in practice, like in cryptography, when you're using an RSA scheme or some such thing, you don't want the problem to be such that it works, it's worst case hard, that it is correct all the time. There is one input on which it fails. I don't want that. I want it to fail on every single input I care about. So you want it, in fact, you don't even want worst case hardness, you want it to be as hard as you can get. Basically, if it's computing a Boolean function, it should be just as bad as random guessing. So certain applications actually require you to have functions that are strongly average case hard. Not even mildly. You won't be happy if you come up with a crypto system that says 10% of the time it will guarantee security to you. You want such things. Yes. So what we want is to ask, what we want typically to start off several cryptographic protocols is strongly average case hard functions. And in fact, if Ramprasad has his original plan for complexity, I think this is what he will prove. He will show that if there is a strongly average case hard function, suppose I have that function in my hand, using that I can construct pseudo-random generators. This is a theorem which we will prove by the end of the course. So if you had such a hard function, you can do nice things out of it. You can build nice objects which can be used for cryptographic purposes. But now, then as complexity theorists, we can ask the question, okay, you can ask, okay, if I have a strongly average case hard function, then I can do things with it. But typically all our theories, if you look at the theory of NP not equal to P, they are only proving you worst case hardness. They are not proving any form of average case hardness, whereas even among average case hardness, what we will need for cryptographic purposes is strongly average case hardness. It seems a bit unreasonable. On one hand, the whole theory that we are building up is only trying to prove worst case hardness, whereas when we build cryptographic protocols and all, we want functions which are even much harder. The natural question that comes is hardness amplification. If I give you a function that is worst case hard, can I from that construct a function that is another function that is strongly average case? So that to tie. So that's the question which comes up constantly in complexity. We'll ask, can you amplify hardness? And if you can do this, then the current study of complexity is well justified. It's okay to study worst case hardness there, because if once I show some function is worst case hard, this sort of amplification process will take that worst case hard function and convert it to a strongly average case hard function, which is what I require for the cryptographic applications. So what we want to ask is, give me a function that certainly the worst case hard function need not be strongly average case hard. I'm just asking, if you give me a worst case hard function, can you get me a strongly average case hard function? And this question makes perfect sense. I just want to motivate the question. So most of this lecture will be motivating the setup, and then there'll be finally we'll come to one problem statement, and you'll clearly see that's MWM. We'll just apply MWM and wrap up the lecture. Okay. Any questions so far? What we will do in lecture today is so there are places where you can do this hardness. It's not true always, but there are some settings where you can go from worst case hardness to strongly average case hardness. And what we will do today in lecture, we will in fact study a theorem which is going to try to prove average case hardness, mildly average case hardness to strongly average. We will only go from here to here. There's a long step to go, but we will try to show how to go from here to here. Even that you won't do all the parts. We will do one part of it in which MWM fits. The rest of the part is there in the notes.
Can we go from there?
There are setups where we can go. If I have time, I'll talk about it. There are setups where it's not true always. We do not know how to do this for NP complete problems and all. These are very different. Even what I do will not happen in the big problems. Like suppose from given that SAT is hard, I don't know how to construct other problems that are hard. Problems which are much lower in the complexity class are either much lower or much higher. That is, problems which are hard for exponential or E, then I know how to move from one to another. Okay, so we'll ask a simpler question. If can I go from delta average that was delta mildly average case hard to mu strongly average case hard. Basically, think of this. I have one function which I know cannot be computed more better than 99% of the time. Every circuit will fail on 10% of the inputs. From this function, can I come up with another function that is more or less that I can compute at best with only 51% of the time? Every circuit will fail on 49% of the time. I can boost the hardness from erring on 1% to erring on 49%. Mu strongly average case hard. We'll ask this simpler question. Is the question clear?
So
we are moving. I'm going to ask. Think of delta something, some number like less than 0.1 or so. I'm asking for a delta average case hard function, and think of mu also around 0.1. I'm moving from a function that you know fails on at least 1% of the inputs to I want to move to a function that fails on 49% of the inputs. Okay, and this is the problem Yao solved. Yao actually gave. So Yao gave an explicit construction for this, and it's called the Yao's XOR lemma. By the way, there are multiple things which are called XOR lemma. Yao himself proved multiple XOR lemmas, and this is one of them. To my knowledge, there are already 4 different XOR lemmas. So this name doesn't disambiguate which XOR lemma, but it will be very clear which XOR lemma I'm going to be talking about. So let's actually change the setting. Suppose I have a coin. Let's change. So this is the question I'm talking about. That's the actual question I want to talk about. If we have time, I'll talk about how to do that towards the end of the lecture. But otherwise, we'll focus on this. So now to this question, Yao asked the following question. Suppose we leave computation. Suppose you have the following issue. I have a coin which comes up heads 90% of the time and tails 1%. It's a very biased coin. From this coin, I want to produce another coin. Using this coin, I can use this coin as many times as I want. I want to come up with another bit that is more or less likely 50-50. How would you do this? So let's ask the simpler question. This is not a function or any such thing. I give you a coin or something, some button, which it's some black box thing, which is going to come heads 90% of the time, tails 1%. So it's not a 50-50. It's biased in one direction, but you know it will give heads, it will give tails 10% of the time, heads 90% of the time. From this one, I want to convert it. There are several ways to do it. I'm asking you for one. I want to use this coin several times to produce another coin which is more or less unbiased.
I guess one of the ways would be to, if it is experimented a lot of times, calculate the proportion of, say, getting ahead as number of tosses goes to infinity. It reaches a continuous distribution. Once we get a continuous distribution, we can always get a quantile function.
You can do it. There's a particular thing for this one.
If heads tails, then it's one even, and tails heads, then it's the other one.
So you can do that. You can do what? So this thing is the following thing. That is, toss the coin. If heads tails comes in succession, then call it a heads. If tails heads comes in succession, call it this one, and keep tossing it till one of these two come. It's one of these is going to come eventually. It can't be tail, it can't be head. At some point, you should get a head and tail in succession, depending on which is the first one. By this one, you're actually making it a perfect. You're actually at the end of this is actually converting it into a perfectly unbiased coin. Yeah. So in this case, in the case of the coin, actually I can take a biased coin and produce out of it an unbiased coin. And on expectation, the number of times I have to toss the unbiased coin is like one, is like I need to get the sequence HT or TH. That is, I need to get this one. It's only a constant number of times I have to do this so that I get that particular. Let's ask, I don't know how to get that to the computational setting. That's so basically what have we done here? We've taken one coin, which is sort of which is a biased coin. Using that coin several times over and over again, we produce another coin, which is a perfectly biased coin. Only catch with this is, which is a perfectly unbiased coin. Only catch about this, I would like to do the same thing in the computational setting. That is, think of this f as one function which takes certain bits of input. This it's probably a Beagle counter or something like that. And from that you're producing the other f prime, which is like the other random bit, except that you don't know how many times the number of inputs to that is not the same as the number of inputs. It's only an expectation, you know how many inputs it's going to take. That is, f prime invokes f a random number of times. On expected number of times, it is a constant. It is a constant based on this 90-10, but it could be very, very long. So in other words, that f prime is not a function on a bounded number of inputs. The inputs for f prime are much, much longer than for f. So suppose I wanted to do it. Another thing I could do it is I could just take the coin. I could just take the coin and keep XORing the coin. Toss the coin 10 times and take the parity of all the answers. And then output that as the answer. I claim each time I take parity, the coin is getting more and more unbiased. Do you see that? Let's repeat the experiment again. Let's repeat the experiment again. I'm going to take the coin. The coin comes 90% heads, 1% tails. And I'm going to repeat the coin say 10 times or 20 times. And I output the parity of all the. So if it is head, tails, head, tails, head, tails, then if you count whether you count the number of heads. If it's even, you output the head. If it's odd, you output tails. What is the bias of this coin? Notice this one, this experiment has the number of inputs, number of times I invoke the other coin is a fixed number of times. What's the bias of this coin? Let's repeat the experiment again. I'm taking a coin which comes up heads 90% of the time, comes up tails 1% of the time. And I'm going to repeat it say 10 times, or let's call it k times. And the new coin is going to be, look, count the number of heads in this k times. If it is even, output heads. If it is odd, output this one. So what is the bias of the new coin?
Close to unbiased.
It gets close to unbiased. So I don't know if you guys have ever seen Fourier analysis. Sometimes they go from the 0-1 basis to the +-1 basis. And I'll give you proof of this, and it will be super simple once we do this in the +-1. Doing it at the 0-1, the way I've taken the problem, is going to make it really messy. You only see it's going to flow to half. But let's just do it. So let's call heads. Let's call heads -1 and tails to be 1. Let's do this mapping. So what do we have? We have expected each coin, let's call it X. Expected X is basically this. If it's an unbiased coin, this will be 0. If it's a biased coin, this is going to be in our case 0.8. It's going minus 0.8. It will, yeah. So this is going to be a number. This is going to be a number between -1 and 1. You agree with me? Depending. If it's -1, it's perfectly. All the time it's coming up heads. If it's 1, it's coming all the time tails. 0, it's a perfectly biased coin. Now, expected xi is the bias of. Expected x is the bias of this coin. If I toss the coin k times, I'm claiming this exactly is the expected. This is the bias of the. Because.
Yeah, because independent, so like it will product up and
it will product. Yeah. So in this world, but you agree this is the bias of the coin which I'm tossing k times, because what was parity in addition parity in check counting the number. When I go to the plus minus world, becomes multiplication. So this is exactly expected. So let's call this to be rho. Rho is some number between -1 and 1. This is expected x to the power k. That's rho to the power k. And that fact that k, as you go make k and k larger, rho to the k is going to 0. And this exactly tells you why this coin which you toss k times becomes more and more unbiased. And how the larger k you take, the better and better the coin becomes unbiased. Is it clear? This is a full proof of this is the bias of the coin. No? So it's going to come heads with 1 plus rho by, you have to find out whether rho is positive or negative. Let's assume rho is positive. Flip the experiment 90 times heads and 10% times tails. Then this is like half plus rho power k times heads and half minus rho power k times tails. So it's almost an unbiased coin. So, and that process is what Yao was calling the XOR process there. This happened to work for information theoretical bits. Yao suggests, why don't we do the same thing? If I have a function on n inputs, let's come up with another function on k input bits, which is just going to take the XOR of the function and ask how hard is this function. So let's save the question. So suppose f is a function 0,1n to 0,1. I'm going to define the function f XOR k to be the function. And Yao's thing exactly gets inspired by that experiment which we did there. Is another function to 0,1, which is what? Which is going to map the input x1, x2, xk. Think of let me put the superscript, because each of them themselves is an n-bit function, n-bit input. You're going to map it to the XOR of fxi, I going from 1 to 2. And Yao asked the following question. Suppose this function was mildly average case hard, then is this function actually strongly average case? And motivated by that example. Clear? And Yao's XOR lemma is basically a theorem which sort of proves this statement. So lemma which by Yao's XOR lemma basically says the following. F is delta mildly average case hard against circuits of size S. Then f XOR k is gamma plus 1 minus delta to the power k hard, strongly average case hard. That's more or less what you should be expecting, 1 minus delta to the power k. Strictly speaking, you should be expecting 1 minus 2 delta to the power k. It's 1 minus delta. If it's delta mildly average case hard, the bias is actually 1 minus 2 delta. And I think if you do the proof right, you will get 1 minus 2 delta. But for me right now, delta, mu and all are constants. I just want to move from, 99% to 51%. I haven't yet said gamma. So out here there was no gamma. This bias completely determined this bias. But notice here it was we were working in the information theoretic regime. There was no something called circuits or anything happening. Here what I have to also mention against what type of circuits. Ideally, I would like to get circuits of size S itself. The proof doesn't work against circuits of sizes. the hardness is against this weaker class of circuits, circuits of smaller size. Against circuits of size, order. Good. Right now I have it as this. It's going to be wrong. Don't think this is right, but anyway, let's see. So notice that if ideally I would like gamma to be 0. But then I pay penalty over here. Basically, then the size of the circuit becomes very, very small. So you want to get the size of the circuit to be reasonably large compared to that. Sorry, this is there. Okay. It seems a bit counterintuitive. Why should the function on more inputs be harder against a smaller circuit class? But this is all that we can prove. I'm not saying this is the truth. The truth might be that it is still hard against even circuits of size, yes. This is what we know how to. Questions?
Could you please repeat why what made this different?
Which different?
I think you said something about
No. So that proof doesn't work exactly over here. That proof was a completely, they were independent. It didn't talk about circuits and all. It's just talking about the bias of a coin. I would like to do exactly emulate the same thing in this setting. I don't know how to do that. And Yao, inspired by that, came up with this construction, and then he proves this weaker result than what you would get from them. And it is weaker because the circuit size is, this was hard against circuits of size, yes. This has become hard against a smaller class of circuits. Notice the function has become on more inputs, but the circuit size against which I'm proving hardness is on a smaller circuit class.
So two questions. The first, why is like stacking them one after the other not working?
It's not a Boolean function, no. Firstly, I want a Boolean function.
It's still a Boolean. No, I'm just
Stacking and taking parity.
Yeah.
Yeah, but how do we prove it? Yeah, the question is how do you prove that? That's exactly what this is. Yeah, stacking them one after another and taking their parity.
Yeah. So yeah. So why? I was saying that why won't the same proof go through?
Why does the same proof? Let's try to do the same proof. Why does the same proof go through? How would we do the proof?
Yeah, I see. I see the problem. Monitors. No.
Yao wanted to do the, by the way, we do not know if Yao actually proved this because Yao is credited to Yao. There's no paper of Yao which has it. Yao mentioned it in a conference talk and hence it's credited to Yao. But Yao being Yao, we expect that he actually did. Yao, there are a lot of theorems which are credited to Yao, which he gave it in conference talk, which he never proved them. These were proved by subsequently others. The proof which we will be seeing is a proof by Infagliasio. This one is a proof by Levin. There's different people have written papers trying to prove what things Yao did. Yao was a remarkable person. Andy Yao is one of the fathers of cryptography. He was at Princeton for a long time. He's currently in Tsinghua University in China. So Yao was motivated by this, but of course, but he had the formal statement. He had the statement. I mean, he had a proof and stuff. Everything over there. It's unclear how to run the whole proof because where are you using? How are you using the fact that it is hard against the circuit of size? Yes, in our proof. That proof was oblivious to all of that.
So again, as you said that the proof was oblivious to the fact that how we are getting our biases out of it.
Yeah.
So again, very naively thinking, getting like doing it for all of those random inputs is same as doing it on a hypercube of size of size nk, right?
Yeah, you're hoping that You're hoping that because you know that this function, the original function, is hard on some delta fraction. On delta fraction of the inputs, it's messing up.
Yeah.
You're hoping that when I pick a random input of size kn, there's a good chance that you will see those delta fraction of input somewhere along this. And even if one of them is, then even if in a parity, even if one of them you are not able to guess correctly, basically you have lost all control of parity. That's what the nice thing about parity. It's a parity of n bits. Even if you 9 of them you get it correctly, the last one you have just a 50-50 chance, it kills parity completely. That's the hope. But how do I show that? In fact, that's where we will go into the proof now. We will see an aspect of this proof where I don't to try to see how to implement this procedure. I need to show that delta fraction of it is sort of corrupted, and I want to base it out of that. I don't know how to get this. Well, Yao proved this statement. Yao proved this statement. And we would want to implement exactly the proof that we gave here. And yeah, we don't know how Yao proved it, but the proof of impagliazzo, which I will going to do parts of it right now, will actually be exactly along that direction. We now see a proof, a part of a proof due to impagliazzo. And it is basically trying to make that argument go through for this. So impagliazzo, so we will I will make a few definitions before. Let's look at the function f. That's assume the input space. We are given this function f on the and you're working against circuits of size s. And let's assume f is delta average, mildly average case. What does that mean? That means whenever I produce a circuit C of size S, there is a delta fraction of inputs in this space where that circuit gets the function wrong. That's what it means, it's delta mildly average case. Now it could be that so for every circuit C, there is a delta fraction of inputs on which it messes up. But this set of delta fraction of inputs that it messes up could be all over the place. That is, each circuit could have a different place where it messes up. Impagliazzo, I want to ask the question, is that really the case? Is that the case? Or is there one set of inputs, which is now going to call the reason talk about hardcore set? Is there one set of inputs where basically you can't do better than random guessing? You can only do 50-50, and the rest you can compute. So suppose the function had this feature that there was some fraction of places where you couldn't get the function better than half, and then the rest was all you will get it perfectly. This will tell you that every circuit possibly gets it correct there, and here it's going to get some 50% wrong. So if this set was like 2 delta size, that will explain why the function is f delta mildly k set. If there is a hardcore set on which every circuit of size S fails to get better than 50-50, there's one set S that fails to get it better than 50-50 for all circuits of size S, then that set S is the reason why you're going to get a delta mildly, because I don't possibly get it correct everywhere else, but here I'm going to get it wrong. And here is, you'll get it correct at most delta fraction of the time, because it's a set of size 2 delta, and that will explain the delta L. So, Impagliazzo asked this question because he wanted to make the proof that way. He wanted to say, there is a hard part. If the input comes from this hard part, then I can talk about. We don't know the input comes from this hard. In doing that proof, if you remember, we had this proof out there. We wanted to say if the input is hard, I do not know what does it mean to be the input is hard, because for each circuit there's a different hard input. Whereas this is sort of trying to make talking about hard inputs irrespective of the circuit. It's changing the order of quantifiers. And it's important here. The original order of quantifiers was every circuit C, there exists a set of inputs on which it fails. So it's a different set of inputs on which every. What I'm going to now, I'll define it formally. What I'm asking is there a single set of size 2 delta so that every circuit of S more or less fails 50-50 on this. I've changed the order of quantifiers, and that's a very important step. That is what will help me to do that step. Then I can say, given a particular Xi, without looking at a candidate circuit, I can say, is that come from the hardcore set or not? If it comes from the hardcore set, then I'm in good shape. Then I know you cannot compute it. It is a path to the making that proof both.
Seems very counterintuitive that something like this should exist.
And by the hardcore set, we will prove this. We'll show that actually there is a hardcore. So let's say what's define a hardcore set. A set H, subset of 0, 1, n, is a delta hardcore set for F against there are two inputs to it. Delta. It can't always be perfectly hard. So let's call it, what give it another. I use gamma already, I use gamma. Let's call it low. Hardcore set for F against circuits of size S. If for every circuit of size S, every circuit C of size S, probability f of x equals C of x. But I'm not considering it on the whole set, I'm considering it only on the hardcore set, is at most half plus rho. And this should be now obvious. Let's write one statement. Let's if H subset of 0, 1, n is a gamma hardcore set for F against circuits of size S, and furthermore size of H is at least 2 delta, the fraction of the whole universe. Then what can you say? You can say F is how winding is hard. Suppose I told you that there is a hardcore set for a function F. Then can you say F is some mildly average case hard? Because every circuit C is going to get at least half minus rho fraction wrong in the hardcore set. And then what is the size of the hardcore set? 2 delta. So it is going to get at least half minus gamma fraction of the 2 delta thing wrong. So that is delta minus, that's, what is it? It's delta minus gamma by. So it is 1 minus 2 gamma. This mildly average case. What I want to ask is the other way around. So certainly if there is a hardcore set, then it is mildly, and the hardcore set doesn't have to be very large. If it is the hardcore set, if it's like 2 delta hard, you get around delta mildly case average hard. Certainly this direction is true. What implication asks is the other direction true. If a function is delta average case hard, does it mean that there is actually one hardcore set that explains the mildly average case hardness?
Yeah, just a bit, why is this implication true?
Why is this implication true? Take any circuit size of size S. You know it fails on the hardcore set on at least half minus gamma fraction. And the hardcore set is of size 2 delta. Therefore, it fails on at least 2 delta into half minus gamma. This is almost definitional, like I set it up. So it is stating that forget, ignore how the circuit behaves elsewhere. Out here, it behaves like basically a random coin. And then basically you get half of it because it's 50-50. On the face of it, it's very counterintuitive. Why should hardness be focused on? Why is there a hard part? One hard, that's why it's called the hardcore set. This is the reason why the function is hard. There's one part of the input. It could be, of course, the entire part of the input. You could ask, is it hard everywhere? Or is the definition of hardcore set clear? Of course, something is hardcore set, something is hardcore. If a given function has a hardcore set, it's easy to prove it's mildly average case hard. That's just this direction. It's unclear why, if a function is mildly average case hard, then there exists a single hardcore set for it. But this will answer Akash's question. Now you can do the proof which we have. So because now you can go back to yours XOR lemma. Suppose the other direction was true. Suppose for every mildly average case hard function, there was a hardcore set. Then you can now go into that proof x1, x2, xk. If even if one of them falls into the hardcore set, no circuit can guess it well. The circuit is going to basically do a random guess, and the parity is going to get completely messed up. It puts it back into that problem. As long as one of the points you're not able to predict it, it's going to kill the parity. And that's exactly what's happening. And that's because I can now talk about the hardcore set without talking about what is the circuit. Let's flip the order of quantifiers. Several times this will be the hard part to study complexity. That is, certain things will happen in a particular order. You want to flip the order of quantifiers, and this is usually not an easy task. And implying the hardcore set lemma, which I haven't yet stated, tells me that an other direction is also sort of true. That is, for every mildly average case hard function, we will actually construct a hardcore set. And if the motivation clear, it is exactly to prove Yav's XOR lemma. Once we have the hardcore set lemma, Yav's XOR lemma proof should just go through. There should be no reason. We should see it why it goes through. It's so we can implement that whole proof. Okay, I want to do this. Basically, I have to state in fact the hardcore set lemma, and once we state it, it will be clear. It will be an application of multivariate weight update method, and we'll immediately get it. But it's just the whole setup. First, the very fact that improviser could believe that such a converse could be true is quite remarkable. Why would there be a single part of the function? If something is mildly average case hard, he's saying the only reason that happens is because there is a core where the function is perfectly hard, it's 50-50 hard, and that's explaining the whole hardness. It's not like each one, for every circuit, the hardness comes from a different part of the input. Little bit of notation before I state hardcore set lemma probably. But essentially the lemma is in some sense the converse to the above statement. So the lemma we won't be able to prove it. We can also prove it. If I put it as a hardcore set, it will be easier to work with something called hardcore distributions rather than hardcore sets. These are a more relaxed form of hardcore sets. So let's first move from that and define that. The hardcore sets. Hardcore distributions. So we call okay, let's D be some distribution on 0, 1, n. Think of, I will call this distribution to be, I'll say D is delta smooth. Yes, yes. Delta smooth is nothing in the support of D gets a very large weight. All I mean is X, the probability that if I sample X according to D, this X is equal to X should always be less than delta by N for all X. We want to be done with, I want it to be sorry. For all X and 0. That no single point takes too much weight. With the no single, so notice as the unit, it can a distribution can be of various types. A distribution could be just focused on one point. This rules out those. This certainly rules out. So let's just to get our hands dirty, let's see a few examples of this. I want to first let's do a few observations. Observation 1. I want to see the uniform distribution on n bits. Is delta smooth for all delta in 0, 1. Zeros.
So obvious because it is delta is equal to 1.
Yeah, it's clear. Also, distributions which are, suppose you take a set of size delta to the 2 to the n, and then just take the uniform distribution on that set. That's also yes. Yeah. So let S be any subset of 0, 1 to the n, and size of S larger than or equal to delta 2 power n. Then the uniform distribution on S is also delta smooth. Suppose here, and I have two distributions, say D1 which is delta smooth, D2 which is delta smooth, and I take a convex combination of them. What do I mean by that? I first toss a coin P. If it comes up head, I toss a coin, possibly a biased coin. But if it comes up head, well, with probability P, I go into D1. With probability 1 minus P, I pick something according to D2. I want to claim a convex combination of delta smooth distribution will also be delta smooth because each one of them is less than 1 over delta to the n. Therefore, if I cut a convex combination of them, that will also be. So all I want to say is the set of delta distributions is actually a convex set. The set of distribution is a convex set. It forms, it's in the simplex delta n over the 0, 1 to the n. This is a smaller body, but it's also a convex set. Want to say the set of delta smooth distributions is also delta smooth. is a convex set, which is stating any convex combination. And one thing which we will not need, but is also true. Now, because it's a convex set, you can think of it as a every distribution is basically a point in a 2 power n dimensional space. I tell it the probability for each of the points in 0, 1 to the n. It's a point in the first quadrant in this 2 power n dimensional space. In fact, in which all the coordinates sum to 1. That's the one. And this is some convex subset of that particular delta S3. It's in this triangular region is sitting. This is the region x plus y plus z equals 1. And its set of smooth distributions is some convex set within this part. I want to further claim, because it's a convex set, I want to say it actually, any point, any smooth distribution can be written as a convex combination. These are, by the way, these are called delta flat distributions. Because they are delta smooth distributions that are arising by taking a flat uniform set of size at least delta 2 power n and taking a uniform. So they're called delta flat. It's a special case of delta smooth distributions. I want to say that any delta smooth distribution is a convex combination of delta flat distributions. In that convex set, this is some convex set over here. I want to claim the corners of the convex set are all delta flat distributions so that every other point is a convex combination of these guys. It requires a proof. I'm going to take it with. We are not going to need it, but this is just something useful for you to know. That is, without loss of generality, any delta smooth distribution can be assumed to be a convex combination of delta flat distributions. Ready to state as a hardcore set now. It's the converse of the statement which we wanted to prove. The converse of the statement that was obviously true previously. So let F be a delta mildly average case hard function against circuits of size S. Then for all gamma in 0 to half, there is an delta smooth distribution H, calligraphic H, such that F is gamma strongly F. Rather, how did I define hardcore sets? Definition of hardcore set. It's called row hardcore set. No? Let's use the word row. Let's use the simple row. That last one, that's that, which is row hardcore for F against circuits of size, order, goes for S for log work delta. What do I mean by that? That is, if I pick an X according to the hardcore distribution, then that is for all circuits, let's call the size S prime. For all circuits C of size S prime, probability f of x equals C of x is less than or equal to half plus. The only difference is instead of a hardcore set, I'm putting a hardcore distribution over. And by the statement that I said, if there's a hardcore set, there has to be a hardcore. A flat set is what I wanted to get. It is a true, but we will clearly prove this. Is the statement clear? This is the statement which we wanted to prove. Any questions on the statement of the? I want to say this is boosting. Suppose I give you a function. Let's do the converse. Let's do the converse state that there is no hardcore. That is, what should we prove? We will prove that for every delta smooth distribution H, suppose we'll prove the converse of the statement. That means if this is not true, that is not true. What does that mean? For every delta smooth distribution, there is a circuit C which gets it better than half plus rho fraction of points. Then I want to claim there is a circuit C which gets it good on 1 minus delta fraction of the points. This is almost boosting except for this fact that these are smooth distributions and all coming into the picture. This is exactly boosting. Let's look at the contrapositive of this, not the converse, the contrapositive of this. The contrapositive of this is stating that if for every delta smooth distribution, there exists a circuit that does better than half plus rho, then there should exist a circuit that does better than, gets it right on 1 minus delta fraction of the points. This is exactly what we did in boosting, from weak learning to strong learning. Except for the fact that the distributions we considered there were all distributions, not. We said if on every distribution you can do better than half plus gamma, then I can get it correctly on the distribution with 1 minus delta. Here it's not every distribution, it's a smaller set of distributions. It's only on smooth distributions I'm getting it.
But that is not a problem, right?
Huh?
It's not a problem.
It's a weaker assumption than boosting. No? Boosting guaranteed that if for every distribution I'm able to get it. So let's look at the algorithm for boosting.
We can always take projections.
Yeah, so because we know how to do projections and because that is, when did we use it? We had to, each time the set, if you look at the boosting algorithm which we did last time, we came up with a distribution and queried the thing on this. Tell me as the algorithm that does better on it. We had to give it only, it would be an arbitrary distribution. But we also show that we could project it to a convex set and do it. So that's why I had this one, I done this projection. So what we'll do is we'll project it to that convex set. And the convex set is a set of smooth distributions. We'll just project it there. Notice all of this, the multiplied weight of that method is not, I'm using it in my mind, it's for the proof. I'm never using it as an algorithm over here. Of course, you can use it as an algorithm and get to this one. The multivariate array, which was introduced as an algorithm, is being used in the analysis of this. I'm claiming that if for every smooth distribution you give me a circuit that computes it, then I can construct another circuit like this. And why did the circuit size go from? So for every smooth distribution, you gave me a circuit of a particular size. Then I'm constructing another circuit of this size. Why is this circuit larger than this? Because if you recall, the circuit that I got here took several such circuits and took the majority of them. So several was how many? It was exactly a log 1 over delta fraction. So it took log 1 over delta fractions of size yes, and it had to get majority. So you had to put the majority circuit on it. That was an extra row square. That's all. The statement is completely given by our hardcore set, by our boosting algorithm with the projection. It just took us a while to come to this and then realize that boosting will satisfy this. Of course, Impagliazzo did not have boosting. He discovered boosting. He wrote the statement and also then came up with the boosting algorithm to solve this problem. He did not know Freund and Shapiro had done it independently and a couple of years prior to his work. But even from here, realizing it boosting takes a minute, but once you write the contrapositive, it should be clear that this is boosting. And that's basically the proof of Impagliazzo's hardcore set lemma. Then from this, you can prove Yau's hardcore set lemma and go back here. Any questions on this? The whole thing is a setup for where to use boosting, and then the multivariate weight update method comes here. In fact, Impagliazzo in his proof, in his paper, used two proofs for this lemma. He gives the proof which we said, which is boosting. And then there's another proof which he actually credits to Nissan and says, no, Nissan proved it, and he gives a proof using game theory and duality. So Piyush, when he is doing duality, will once again come to Impagliazzo's hardcore set lemma, and he will give the proof not using multivariate weight update method, but using LP duality, he will prove the same state. Questions on this? So we didn't prove anything, it's just a setup. The whole thing was reducing one problem to another. Finally, we reduced it to a problem that we knew how to solve and we stopped the whole thing. But actually, on the other hand, if you look at it, the whole thing is quite a remarkable set of reduction. The fact that you could go through this line of thought is quite remarkable that one can do this. Yao, for his fact that he could imagine such a thing would happen, and then Impagliazzo then come up with this alternate proof of this is also quite remarkable. Questions? So, this is the statement seems Yao's. So Yao's hardcore set lemma, Yao's XOR lemma seems as a very obvious statement. The statement of, but that actually took far and wide true. Impagliazzo's hardcore set lemma on the face of it actually seems that why should such a statement be true at all? Why should, if something is hard, you are saying if something is hard, that means every circuit has some place where it fails. I'm claiming that can't be the case in the article because there's one single place where every circuit fails, and that's the reason. This is quite a remark. Why should such a thing be true at all? But truth is very obviously looking on Yao's XOR lemma. We need to take this Impagliazzo's hardcore set lemma, which is not obvious, but the other has a simple proof. And then you string them all together, you get Yao's XOR. Questions? A couple of things you guys wanted to know. So there's this whole field of going from hardness amplification, all of this. Just did one board cycle, barely board. This was more or less the beginning of the lecture. Why was all of this motivated with? Because typical study in complexity is trying to prove worst case hardness, whereas what we need for various cryptographic applications are actually strongly average case hard functions. We wanted to ask the question, can we move from worst case hard to strongly average case hard? And we asked a simpler question where can we move from mildly average case hard to strongly average case hard? And that we showed that sometimes you can do this. Sometimes you can do it. By the way, this reduction does not work in NP. It works. The problem is you have to do parity. You have to take, sometimes you're taking whether membership in the language, membership not in the language. Parity means to do this. And this is not clear. So you cannot do the hardness amplification in parity using the proof which I said. If parity is the combining function, I do not know how to do it. There's an alternate way of doing it using recursive majority, which is, this was Ryan O'Donnell's PhD thesis, where he used recursive majority to do it. So this hardness amplification doesn't work in NP, it works in either in P or in X or E or so, and that's sufficient for some of the cryptographic applications. What's the other thing I wanted to say? It leaves open the question of how to go from worst case hard to mildly average case hard. So that was also done. That was done by Bobby, Fortno, Nissan, and Vickerson moved from worst case hard to not Bobby. Impaglazo and Vickerson moved it from worst case hard to mildly average case hard, and this one moved it from mildly average case hard to strongly average case hard. And this is all going via the XOR lemma. There is yet another way in which you can do this, and this was done by work by STV, Madhusudan, Luca Trevisan, and Salil Vadan. They actually constructed pseudo-random generator. In fact, the title of the paper is called Pseudo-random generators without the XOR lemma. They actually did not use the XOR lemma. They used error correcting codes. I'll just give a 5-minute sort of thing to what they did and stop with it, because it's an extremely beautiful application of error correcting codes. So, do you know why? Have you guys seen what are error correcting codes? What are codes and stuff? It's just a way to encode. What's a code? A code. It's to answer this problem of you're sending in a message. It comes out the other side. This is what happens when you speak on a telephone or something. You speak. It's getting encoded in some format. It goes through a channel, comes out at the other end. And in principle, you could put something called the encoder here, and you could put the decoder here. Why do we put this? Because we don't send the raw message as it is, because this channel could be corrupt. It could flip a few things. So even if it flips it, the encoding is adding some redundancy to the message, so that even if some corruptions happen, the decoder can get rid of the corruptions and put it back at the other end. So the physical channel is just this. This could be either your telephone over which you are talking, or this could be your hard disk on which you are writing stuff. You don't write it in the raw form. It's not stored exactly in it. Some redundancy is added, so that in the writing process, a redundancy is added, so that when you read it, it will fix it. If there are a few errors there, it will just fix it each time. So this process need not be a temporal thing. It could also be a spatial thing, like a hard disk. So what is a code? A code is some object which takes k message bits and adds redundancy, and typically n is always greater than or equal to k. In fact, greater than, you want to add redundancy. It takes a k bit message, blows it up to slightly larger, gives an n bit message. That's the code. And what's the rate? The code will have two important properties. One is called the rate, k by n. This is basically the amount of information of the original message in each bit of the output message. And typically, the more redundancy you add, this is going to become smaller and smaller. So sometimes for performance, we want rate to be as close to 1 as possible. You don't want to add redundancy, but you don't want to. Of course, rate of 1 is infeasible. It's the same message. You would like to, but rate, we want to keep it as close to 1 so that you don't put too much redundancy. But the other thing, which is most important, is what is called distance. Distance is the minimum. Take two x1 and x2, or rather xy, in 0 into k. You take two such original messages, and look at the distance between C of x and C of y. How far they become.
Having this.
Hamming distance. Let's work with Hamming distance. This is delta Hamming. Okay. Suppose there was a code with rate 0.9 and distance say distance say 0.4. What does 0.4 mean? I do not know whether these feature numbers are achievable. But
Distance has to always be.
oh, sorry. Then I will make it fractional distance. I'll divide everything by n. Yeah, I'll make, when I mean distance, it's usually an integer, but we will make it fractional. We'll make it fractional, we divide it by n. So usually d is used for distance and delta is used for fractional distance. That is used for real distance. Absolute distance is used for fractional distance. Now, suppose you had a code, or let's even work with this one. Suppose you had a code with 3 bits. I make a distance to be 3. Now I claim, once I do this, every message, if there's just one, if you tell me that, of course, if this is going to flip everything around, I can't guarantee anything. It can flip something to something else. But suppose I get the guarantee that this one never flipped more than 1 bit at any point of time. Then I claim if I had a code that flips only, that in which any 2 code words are 3 apart, then even if it flipped 1 bit, I can easily recover. Because even if it's 1 bit, so basically what is happening, what's the distance 3 mean? If you look at the space of, this is the space, this is not the original code, this is the space of 0, 1 to the n. This is not the space 0, 1 to the k. So not all points here are the image, not all points here are the image of this. There are only 2 power k image points sitting here. And what does distance tell you? Distance tells you that any 2 of them are at least d apart. Now, in the corruption, while corrupting, suppose this guy got corrupted to something else. So you sent in C of x, but it got corrupted to something else. As long as this guy, the corruption thing, lies in a ball of radius b by 2, you uniquely know which guy it had come from. You can just go back to that one. I don't know how to do it algorithmically, but at least combinatorially, it's clear why this should happen. That is, if the number of errors here was always less than the distance by 2, then you can recover. So that's the heart of error correcting codes. You want to design codes in which rate is as close to 1 as possible, distance as large as possible. What sort of codes you can put. And this need not be over the Boolean alphabet. This can be over a larger alphabet and all of this. Okay, is the coding question clear? So this is how that's codes. And there are codes which are, so let me tell you another code. Maybe not time. 9 minutes I should talk about. Let's look at what is called the Hamming, the Hadamard code. It's a code from 01k to 01. Actually, it makes it very, very long. The redundancy is humongous. It's like the number of message bits is exponential. What does it do? It takes any symbol x. It's going to output a 2 power k long string. What is a 2 power k long string? It's going to give me the dot product of x with every string of length 0, 1 to the k. It has 2 power k bits, and these are the 2 power k bits. It's going to give me the dot product of x with every possible. You follow what the coding and encoding is. It takes a k bit message and outputs a 2 power k bit message in which the 2 power k bits are indexed by themselves points in the Boolean hypercube of size k. And what is the point? What is the bit you give as the location corresponding to a? You give the dot product of a with this message x.
But the dot product need not be.
I'm doing everything in GF2.
Okay.
I'm doing it in GF. Let's work. We are working in the field in GF2, and everything multiplication, addition, everything is happening in GF2. Okay. Yeah.
How are we ordering the?
There's some ordering. I'm going to give some ordering, and if I know a location, I know what is the bit. All I need to know is what is the bit and what is the A that corresponds to it. So think of some lexicographic ordering of the A, and I'm going to give it that way. The rate for this is terrible. The rate for this is k by 2 per k is terrible. It's not anything approaching 1. But let's look at what is distance of this code. So I'm asked, the rate is terrible. The rate is k by 2 per k, and this is going to 0 as k goes to infinity. This is actually very, very bad. But let's look at distance. Rather, fractional distance. So delta of Hadamard. So that's what I'm asking. I'm going to take x and y, which are two distinct points in 0, 1 to the k. And I'm going to ask what is the probability that if I pick a random a in 0, 1 to the k, ax equals ay. Rather, ax is not, distance is ax not equal to differ. Why is this? I'm asking how many places they are going to differ. That's exactly for what fraction of a's are they going to have two different values. This is exactly the fractional distance. Agreed? So let's write this in a slightly different way. This I claim is the same as probability A inner product x minus y is not equal to 0. Where x minus y is a non-zero vector. If x and y were the same, it is a 0 vector, and this will be 0. Which is clear. If the two things are this one, the distance between them will be 0. But if suppose xy is a non-zero vector, how many a's are going to have 0 dot product? How many a's are going to have 1 dot product? I give you one fixed string, non-zero string. If it was a 0 string, every string will have dot product 0 with it. Suppose I give you a non-zero string. How many a's will have 0 dot product with it, and how many a's will have 1 dot product with it?
1 by 2 minus.
Huh?
1 by 2 minus.
I claim half of them will have
Half and
half of, yeah, exactly half.
it's 2 by k minus 1 by 2.
Yeah. So this is half. So this code has fantastic distance. These two code words are far apart at half from each other. So as distance wise, it's an amazing code. Rate wise, it's a terrible code. They happen to be codes in which the distance is also constant. The rate is also constant, not inverse exponential, in which you can get distance not half, but half minus rho for every row that you have our choice. Now, suppose you had such a code. Okay. So far I said, so the Hadamard code has distance half, which is the best distance one can hope for a binary code. Why that's the best, we'll come to it later. This one, let's defer that off. But it's the best distance you can have for a binary code, but its rate is terrible. But there exist other codes which have very good which have distance almost half. It is half minus rho for any row, and distance and rate which is a constant, which is a function of rho, not exponent, not going down in k or anything. Okay, let's take such a code. Let's say one thing and I will just stop. Completely unclear what I'm doing right now. So let's C is a code with distance delta of C to be half minus rho, and rate of C is some calling in 1 over rho. There exist such codes. Now let's take a function f on 0, 1, n to 0, 1. This was our worst case hard function. I'm going to think of this function. Let's call it k. This one, I should have used a different k. This code is 0, 1, capital K, 201 capital N. And this is small q. This function I can look at it as a truth table. And think of the reason why I'm calling that capital things are all exponential in the small things. So I'm going to think of this function as the input to that code. The code, and I'm going to run the code on it, C, and I'm going to get another function on capital N bits. And this N, I'm going to think of it as 2 power N. So this is a function. So this will be a function f prime going from 0, 1, n 0, 1. Now, what's the distance of this code? The distance of the code is half minus rho. So if there were a number of errors, if I gave you something which corrected it only on less than half the distance, on 1/4 minus rho, or 1/4 minus rho by 2, then I can come up correct this guy correctly. But one thing I want to do is control that. Suppose there is no algorithm that can compute this correctly. Then I claim there's no algorithm that will correct this on more than 1/4 minus epsilon part. Because if I had an algorithm that does this, I can use that algorithm to do this. The same sort of this. Unfortunately, this stops at 1/4 minus rho. You can push that 1/4. You can show that if there's an algorithm that even if there are half minus rho errors here, I can get this correctly. There seem to be such algorithms. These are called list decoding algorithms. There exist codes which are not only this but also have list decoding. That is, they can work against errors which are not delta by 2 but actually close to delta. They can work with this many errors, any errors less than delta. So if you add, so what they suggested was take a list decodable code, apply the list decoding on the message, get this, and this object will be the new function which you would have to be. There's a lot of details missing in this. Some of this might be covered by Ram Prasad towards the end of this competitive course this year. All of this which I'm saying is coming from the paper Sudan Sanvaran. Pseudo generators without the. Sorry.